like in almost every conference, like FAIR and this and that. So I thought that everything about clustering was known, like the classical clustering. This was my feeling. That is why new form of clusterings are coming, like FAIR or some NV-free clustering and all kind of new definitions, right? But good to see that there are still lots and lots of things. I mean, at least.
I guess you're partially correct in the sense that everything that is low hanging is known.
Yes, correct.
And yeah, so people just give up sometimes when it's too hard, like TSP. People had given up 3.5. We are happy with it for a while.
Yes. Correct. Yeah, that's right. Okay, people are joining in. So let's wait for a couple of minutes.
Okay.
We have to be IST. Is the recording, should recording not start? Hello? Who's taking care?
I will start. Gayatri here.
Okay, hi Gayatri, thanks. Okay, I just wanted to know that. Okay, there is. Okay,
no, sure. I just started the streaming because you said couple of minutes. I'm waiting.
Sure. No. I just wanted to be sure that there is.
Yeah, I'm here, sir. I'm here. Yeah.
Okay, thank you. Okay, so let me start with at least telling something about Karthik. So finally, I mean, if I understand, Karthik, you were doing computational geometry, right, in your master's avatar?
Right, and chemistry before that.
Exactly. So it's very fabulous journey from chemistry to computational geometry. Then you went to Israel and you did hardness of approximation, largely.
Right.
Okay, and then you went to US and this love for hardness of approximation continues. So if I have to ask you what you like, making algorithms more or making hardness reductions more? This is my favorite questions to all the people who make such things.
I see. I personally like to find out the truth, and I feel better equipped to do hardness of approximation.
Okay. So given that, now that he feels much more equipped, so we will know what all equipments he uses to prove this hardness of approximation. So yesterday, Karthik gave us a very nice overview of the kind of things which have been being done in clustering and where the field is. And today, he will delve deep into some of these tools and techniques and tell us how new generation of hardness of approximation in metric clusterings are being done. So Karthik, over to you.
Thank you, Saket. So today I want to start with some slightly philosophical overview, which is, I want to sort of put all the problems that we study, which are NP hard, into some kind of perspective based on the notion of approximation. And this is very, very philosophical, so it's hard to formalize it, but let me try. So I want to put things on the spectrum of structure, where on the least structure end, we have circuit SAT and CSPs of large arity, where it's very easy to prove that they're very hard. And even hardness of approximation, even very hard to approximate. And then one of the remarkable results in TCS over the last 40, 50 years is this Pcp theorem, which says that, it's not just any arbitrary CSP, but CSPs of constant arity are still hard to approximate. So you have a little more structure. And then we were able to prove these hardness of approximation results for not just some label cover, some abstract formulation, but like concrete problems like set cover, set systems, natural computational problems that arise from set systems. We were able to prove strong and tight hardness of approximation results. And then what next? We wanted locality. So what about 3-SAT or 3-LIN? We were able to prove tight hardness of approximation results. And at each time, there was a new set of techniques that were needed. Like for set cover, we needed the parallel repetition theorem. For 3-SAT and these things, Fourier analysis came in. So each time when we needed more structure and we wanted to prove hardness for more structured problems, we had to bring in more tools. And then after that, we looked at graph problems. And here we have a tight understanding, assuming the unique games conjecture. And again, we have to bring in a lot more Fourier analysis and a lot more tools into this thing. But then here sits this set of geometric problems whose understanding from hardness of approximation was very, very bad. All we were able to say is that, okay, there is no pitas, but the approximation community is like intensively working on it from an algorithmic point of view. So there is this disparity, like, and as there is more structure, it becomes hard to prove hardness results. And somehow, so we needed tools to understand this. And while the unique games conjecture sort of addressed all the graph problems that we are interested in, giving us tight understanding, there was nothing really to capture these geometric problems. And in particular, like yesterday, I told about clustering. And so there was this need to put forth this Johnson coverage hypothesis. The idea being it's this intermediate problem with very little structure. It's just some set system problem. And yet it implies all these tight results for clustering. So, okay, then we have reduced the problem to proving hardness of something that has less structure, which is always an easier thing to do. And the nice thing is that a weak version of the Johnson coverage hypothesis is just the vertex coverage problem, whose tight understanding we know from the unique games conjecture. So it's not like completely baseless. We at least get something out of it. Okay. So I'm going to, now that we have the perspective right, I want to show how the Johnson coverage hypothesis implies these tight results for clustering. But before I do that, yesterday I promised I wanted to show how to embed things for the K-center problem. And that sort of sets up the techniques that we need for the Johnson coverage hypothesis. So we will revisit the K-center problem, where things were more or less known in the 80s. Here, the input is a point set X, which we want to cluster, and a set of candidate centers S. And we want to sort of identify K points in our set of candidate centers such that the radius to every point is minimized. So if you look at any point X and you cut its closest center, and you want to minimize this distance over all points X. Okay, so we have the K-center problem. And what was known in the general metric, we knew that there is a simple 3 approximation algorithm and that is tight. And we had seen the proof. It was from the max coverage problem, where if the sets correspond to centers and the universe elements correspond to the points that we want to cluster. And in the yes case, there are K sets or K centers, which are all covering it. So it's a distance 1. And in the no case, if there are any K sets we pick, one of the universe elements will not be covered. So you'll be paying distance 3. So that's how we get this result. But now let's try to show things. So we get this 3 in approximability result in general metric. I want to show the same, but now for the L1 metric. So let me try to show how the embedding is done. And I will also make a few comments about how things are done in the Euclidean metric and so on. So all these things for L1, L infinity Euclidean are known in the plane, so in dimension 2. But today I'm going to show it for n dimensions. And what we need is a special case of the max coverage problem, which is the vertex coverage problem, where you're given a graph and an integer k, and your goal is to cover as many edges as possible using k vertices. When I say cover, it means that the edge is incident on, the vertex is incident on the edge. And we know from the results by Karp that this is NP complete to determine if there are k vertices that cover all the edges versus k vertices, any k vertices miss at least one edge. And how do we do this embedding? Well, we're going to do it in Rn. So such that if there is a vertex coverage, then the k-center cost is going to be 1. And if there is no vertex coverage, that means that every k vertices miss at least one edge, then we're going to show that the k-center cost is at least 3 in the L1 metric. Let me make this point already that this is in Rn, but you can also do it in R2, and I will tell how later. The idea is very simple. You think of the bipartite graph between the edges and the vertices. And you think of this as all subsets of size 1 and all subsets of size 2. And when you think of things as subsets, there's a natural way to think of them as points in 0, 1 to the n, where you look at the characteristic vector, where if an element belongs to the set, then you put a 1, otherwise you put a 0 on that coordinate. And now when we do this, it happens that if a vertex was hitting an edge, then their distance is going to be 1. And if a vertex was not hitting an edge, then the distance is going to be 3, just because the cardinality is 2 on top and 1 on below, and there is no matching happening. So just because of this, we have that if we took the bottom as our candidate centers and the top as the points to cluster, and we are in the L1 metric. So we have, naturally, we get that the 3 in approximability continues here as well, because in the yes case, everything is going to be at distance 1. And in the no case, any k guys we pick, any k vertices we pick, there's an edge that's not covered, that's going to be at distance 3. And of course, this is in n dimensions. And so we get this result. And this also gives a gap of 1 versus square root 3 for Euclidean metric, because you have to take a square root. Now, how do you get those tight results for the previous case? Well, you start with planar vertex cover of degree 3. And we know that this is still NP hard. And then you're in the plane, and then you can look at some more specialized embeddings, which give you this distance, because you can always subdivide edges and the hardness continues to hold, and you just make sure everything is like a line. Okay. But the reason I presented this proof is it's going to be helpful when we are looking at the Johnson coverage hypothesis. And for the Euclidean metric, there's more careful analysis of geometric objects that one has to do, but let's skip that for now. Okay, now that we got a flavor for k-center and what kind of embeddings entail, let's go back to our k-means and k-median. Again, here the objective that we want to minimize is sum of distance squared to the closest center for k-means and sum of distance for k-median. Okay. And what we saw yesterday was that, in fact, in the general metric, it's 3.94 for k-means, and that's tight even for L1 or L infinity metrics, assuming the Johnson coverage hypothesis, and you get some strong inapproximability results. I'm going to deal with the discrete case first and then the continuous case. Recall that for the general metrics, you just looked at the set system and 1 and 3, and this gives you, we had the hardness of approximation for max coverage, which was 1 minus 1 over E factor. So in the yes case, you pay 1 everywhere. And in the no case, for 1 minus 1 over E fraction, you pay 1. And for the rest, you pay 3. And if it's k-means, it's like 9 because it's distance square. So you get 1 plus 8 over E. Good. Cost is 1, cost is 3, and we are good. So we get this 1 plus 8 over E result for the general metric. Now, let me again recall what the Johnson coverage hypothesis is. You're given as input subsets of size t over a universe of size n, and you want to identify k subsets of size t minus 1, such that every subset, in the yes case, every subset of size t contains one of these k subsets of size t minus 1. And in the no case, a uniformly random subset. So once we fix the any k subsets, a uniformly random subset in our input of size t is not going to cover any of the k subsets that we picked with probability 1 minus alpha. And this becomes, and if t is 2, this is essentially the vertex coverage problem. Because you want to pick vertices as your solution to cover edges. And the hypothesis says that as t increases, the ratio tends towards 1 minus 1 over E, the inapproximability. Okay. And I'm going to just make this clearer with a picture. But let me state the theorem first that I want to show the proof for. So assuming the alpha t Johnson coverage problem that, when at the tth layer of the Johnson coverage problem, it's hard to approximate to a factor alpha. From that, we are going to construct an input for clustering in the Hamming metric, where we are in log n dimensional space, and we want to construct 2 point sets. such that in the yes case, the cost is going to be n prime. And in the no case, it's going to be 1 plus 8 times 1 minus alpha times n prime. The intuition being, in the yes case, you're going to pick those case sets of size t minus 1, and each one is going to be at distance 1. And in the no case, any case sets of t minus 1 we pick, alpha fraction of them is going to be at distance 1, and the remaining 1 minus alpha fraction of them is going to be at distance 3. And because you're taking square, it's 9. So it's going to be alpha plus 9 times 1 minus alpha, and then you get 1 plus 8 times 1 minus alpha. Okay, good. So, and then what happens is that if we plug in our hypothesis that this is hard to approximate to a factor 1 minus 1 over e, here you get 1 plus 8 over e, and you're in the Hamming metric. So this also extends to the L1 metric. So you get all these tight results. And instead, if we plug in 0.932, which we know already from the unique games conjecture for the layer 2 for vertex coverage problem, here you get the value 1.56. So these are just plugging in the known hardness results. So what's the intuition? The idea is you look at this bipartite graph again, where you have all t subsets on the top and all t minus 1 size subsets at the bottom. So our input is going to be all the things at the top, right? Like, because we're going to get a subset, we're going to get a collection of subsets of size t. And our goal is to find k guys in the bottom, t minus 1. And we think of these as points in 0, 1 to the n by looking at the characteristic vector. So all the things on the top are going to have t many ones, and all the things at the bottom are going to have t minus 1 many ones. And I'm going to refer to this as the Hamming weight. So everything at the top is going to be of Hamming weight t, and everything in the bottom is going to be of Hamming weight t minus 1. And the nice thing is that if a set of t minus 1 is contained in a set of size t, and then you look at their vector characteristic vectors, they're going to be at distance 1 in the Hamming metric or the L1 metric. Whereas if you take two sets, one in Hamming weight t and the other in Hamming weight t minus 1, and one does not contain the other, then they're going to be at distance 3 away. So this is where you get the gap between t and t minus 1. But the point is we are in n dimensions. So we need to somehow go from n to log n. And we don't have the Johnson-Lindenstrass theorem or any of those dimensionality reduction tools here. So what do? We design a communication game. Okay. So we have two players, Alice and Bob. And Alice has a subset of 0, 1, 1, 2, 3 up to n of size t. And Bob has a subset of size t minus 1. So we're thinking of a communication game where Alice holds a subset of size t and Bob holds a subset of size t minus 1. Good. And this is a one-way communication game. So both these players get their inputs and Bob will send some messages to Alice. Okay, so this is the goal. And they both have access to public randomness. So they both can jointly toss some random coins and know the outcome of these random coins. What is the goal? The goal is for Bob and Alice to know if Bob's input is contained in Alice's input. So Bob has a set of size t minus 1, Alice has a set of size t. They have to somehow decide if Bob's set is contained in Alice's set, and they have some public randomness to do this, but only Bob can send one message to Alice. Okay, so this is the game. This is the containment game. And of course, Bob can just look at every element in his set and just send all those elements as they are. So each element can be encoded using log-n bits, and there are t many elements or t minus 1 many elements, and Bob can just send all of those. So he can just send the entire input to Alice, and Alice is just going to then check if Bob's set is contained within hers or not. And you have completeness 1 and soundness 0 in the sense that if Bob's set is contained, then Alice will know for sure that it's contained. And if Bob's set is not contained in Alice's set, then Alice will for sure know it's not contained. So you have like perfect thing. But the problem is the message length is too much. I don't want to send t log n bits. So what we're going to see now is a randomized protocol where you send a constant number of bits, where the constant only depends on t and some error parameter epsilon. So independent of n, that's the important thing. And this will have completeness 1 in the sense that so the idea is the following: Alice and Bob both get their inputs. So let me go back here. Alice and Bob both get their inputs. Both of them toss some random coins, and then Bob looks at the input and the random coins and is going to send a constant number of bits independent of n to Alice. Alice then, on receiving Bob's message, is going to look at the randomness, her input, and the message Bob sent and decide to whether accept or reject. Now, what we want is that Alice always accepts if the set S is contained in T, and Alice rejects with very high probability otherwise.
So Karthik, just to make it clear, when you say public randomness, so suppose they both decide on what you call tossing a coin together, or if anybody tosses a coin from here, other can know the outcome.
So both ways are fine in the sense that both of them jointly toss a coin together and they see the outcome of that randomness, or someone else tosses and they both know the same outcome of the randomness. The main point being they agree on the random bits. Okay. And so here we can make epsilon as small as we want, any small constant as we want, and we are just sending constant number of bits. And in the yes case, if the set is indeed contained, Alice always accepts. And in the no case, she will accept with probability just epsilon. Okay, so we're going to see this protocol. And once I show the protocol, the next thing to see is how this protocol will be used to reduce the dimension of our clustering instances. Okay, so in order to show this protocol, I need an error correcting code. So let Q be some large prime, and we can encode our universe, each universe element in FQ to the log n. Of course, we can do it in F2 to the log n, so we can definitely do it in FQ to the log n. So an error correcting code is just some function which is going to take log n field elements and output C times log n field elements for some large constant C. And the idea is that even if the initial two strings differed on only one coordinate out of the log n coordinates, in the output, when you have the C log n bit strings, C log n field elements, they're going to disagree on most locations. So that is what an error correcting code is. And so let's take an error correcting code. And what Alice and Bob do is first uniformly toss some random coins and agree on a coordinate of the encoding. So they're going to just jointly toss some random coins and agree on some coordinate of the encoding. And then they're going to encode their own sets. So what they do is Bob first encodes. So Bob has T-1 universe elements. So, and each element, Bob independently encodes it and then looks at the ith coordinate and sends the ith coordinate of all the T-1 universe elements encoding to Alice. So Bob has, say, U1, U2, U3 up to UT-1. Then he's going to encode each one of them. So he's going to encode C of U1, C of U2, C of U3 up to C of UT-1. Look at the ith coordinate of all these encodings and then just send the ith coordinate. Okay. Then Alice herself has T universe elements. She will encode all of them and look at the ith coordinate and create the set Ti, which is the ith coordinate of all the universe elements encoding she has, and check if the message that Bob sent is contained in the message that in her own Ti. And if it is, she accepts. If not, she rejects. Okay. So let's
one
look.
thing, Karthik, I did not understand. How does Alice checks whether SI is like
So
her
Bob
set is contained or not? Okay.
Right. Bob will send SI. Bob has a set S, but he's not going to send S because S requires too many this. So what he does instead is he encodes S and then looks at a specific coordinate and only sends that.
Yes. And then what does Alice do on those after getting those coordinates?
Right. So Alice knows the coordinate I and knows basically some field elements. So Alice has received some set. So Alice herself will compute the set Ti based on her input and check if the set she received is contained in the set Ti.
Okay.
If yes, she accepts. If no, she rejects.
Okay. Thanks.
And the key point here being Bob's message is not t-1 times log n, but t-1 times log q, where q is just some large prime, which we'll pick to be some large constant. And the soundness of this protocol, which we will see, is that it is t times 1 minus the distance of the code. Because any two code words can agree on at most 1 minus delta c locations, the distance of the thing, and there are t things in which they can agree on. So we're going to see that it's at most t times 1 minus delta of c. Okay. So this is the protocol, and this is the claims. And now the point being that if we choose algebraic geometric codes, and only with algebraic geometric codes, this value becomes 1 over square root q. So you can just choose q to be any large prime that we want. And in the yes case, Alice always accepts. And in the no case, she accepts with probability 1 over square root q, which tends to 0 as q becomes large. Okay. So now that I described this protocol and these claims, I want to describe how this is used to create the embedding. So we are going to embed every subset to be a vector in 0, 1 to the q times c times log n. Notice that c is some large constant, q is some large constant. So we are really in O of 1 log n, O of log n dimensions. And so every subset, we're going to create a vector in O of log n dimensions. Okay. And in order to define this embedding, let me first fix an I in C log n and a subset S of some cardinality in the universe 0 in 1 to n. So we have fixed a set in the universe 1 to n, and we have fixed a coordinate I. So notice that means that I have to define, if I can define q bits, then I have defined this thing, because what I have to define now is tau of s on the block I. So I really think of tau as embedding into C log n many blocks, each block containing q bits. Now I have fixed a block I, and I have fixed my input s. So I just have to define what these q bits are on the ith block for s. And this is just going to be, you're going to look at the subset S that will contain certain elements. And then we are just going to look at the encoding of those elements on the ith coordinate. So you get basically some field elements. Okay. So again, let me repeat. So you have some subset S of the universe 1 to n. Then we encode it using our function, error correcting code function C that we had. And once we encode it, then we look at the ith coordinate. Now, if the cardinality of S was T, then on the ith coordinate, we're going to see T field elements. And now these T field elements, so now we have to write it. We are going to write it think of it as a subset of Q, these T field elements, and we're going to write the characteristic vector. So on the ith block, we are going to write the characteristic vector of ESI, where SI is the ith coordinate of the encoding. Okay. And let's give an example. Like I'll give a couple of examples. So consider the set S, which is 1, 2, 3 up to T. And now let's look at S1, of course, the first coordinate of the encoding. It's just the same, 1, 2, 2 up to T.
So Karthik, I have a question. I mean, I want to understand what you're doing in this slide with respect to what you described in the previous slide.
Okay, so the previous slide, I described a randomized protocol for this game that I created.
That is over assuming the black box of that code, correct?
Right. There is some error correcting code which you can take black box from the shelf that is known in literature.
Right. So, and you're not going to prove that probability thing. That's also assumed, all right? That
I can.
No, okay.
I can do it, but let me do it in the soundness when I actually need it.
Sure. Now, I've just, so what is it now you are doing?
I'm going to show how we can, I'm going to construct an embedding of the protocol we saw and see how we get points in space.
Okay.
So I'm going to embed every subset as a point in space. So then such that certain distance properties hold. And then I'm going to put all of them together to do the reduction to clustering from Johnson coverage hypothesis.
Okay. Thanks. Yeah.
Okay. So let me just confirm what the embedding does here. So suppose we had the set 1, 2, 3 up to T of universe size n. And let's look at its encoding. And let's suppose on the first coordinate, they're exactly what they are, 1, 2, 3 up to T. So then on the first block, you would write 1, 1, 1, 1 T times, and then all zeros. So you have a block of size q bits, which contain the first T coordinates are 1, and then the rest are zeros. So that's what is here. But suppose let's look at some ith coordinate of, and then on the ith block, you have that the field elements are 1, 2, 3 up to T over 2, and then Q minus T over 2 plus 1, so on up to Q. So you have like ones in the top and ones in the bottom. So then on that block, you write the first T over 2 ones, and then all zeros, and then T over 2 at the bottom. So this is how the encoding would look. You're going to take a subset, and for every subset, you have a large number of coordinates divided into blocks. There are C log n many blocks. Each block is of size Q. And in Q, you write the characteristic vector of their encoding on the ith coordinate. Okay, so this is the embedding. And of course, now we can define a reduction, which is you are given as input the Johnson coverage hypothesis instance, which are subsets of layer T. So you have a collection of subsets of size T. And from that, we are going to create a point set, which is just all the you take the subset and embed it using this function tau. And so you get this collection of points, and these are the points that we want to cluster. And the set of candidate centers are going to be the embedding of the entire layer T minus 1. So you look at every subset of size T minus 1, and then you look at its embedding under tau, and that is the set of candidate centers. And the claim is, of course, that in the S case, if there were k subsets of T minus 1 that covered all of your subsets of size T, then here they will have that after doing this embedding, if you look at the points, corresponding points, then those k points of Hamming weight, whatever they are going to be at distance 1. So for every point in X, you're going to have one of these k points, which is at distance 1. So we're going to see this claim with more pictures. And before I do that, let me make a couple of structural observations that become very handy to convince why this proof goes through. Suppose we have two sets, S and T, and S is indeed contained in T. Then you look at any block I, we have that Si is contained in Ti. Why is this the case? So what is Si? Si is just the encoding of all the elements in S, and you're looking at the ith coordinate. Now, all the elements in S are also in T. So if you look at Ti, you're going to look at all the elements that are there in S and maybe more. And then you're going to look at the ith coordinate of their encoding. And since you're just taking unions and you're just including things, SI will definitely be contained in TI because TI is just contains SI and something else. And now if this is the case, then if you look at the qth block, if you look at the ith block, and you'll have basically two characteristic vectors where of sets one containing the other. So it will be that all the places where SI is 1, TI will also be 1. But on top of that, if say TI contains one additional element, then it's going to have one more in one other place. So their distance is going to be 1. Because wherever SI is 1, TI is 1. Wherever SI is 0, in at most one location, TI can be 1 other location. And everywhere else, it's also 0. So on that specific location that where the additional element is, there it's going to be a distance 1. Okay. So the bottom line is that if S is contained in T and F is of cardinality T minus 1 and T is of cardinality T, then for every block I, we have that SI is contained in TI, and moreover, we have that the distance of after you embed them using tau is going to be at 1. Okay. But what happens if S is not contained in T? Right? Then the claim is that for most blocks I, we have that SI is not contained in TI. This follows from the encoding property. But let me try to first say about the embedding. That suppose you had, you looked at everything here SI minus TI, and it contains at least one element, right? So there is one place where you write 1 in SI, where you write 0 in TI. And by definition, since TI has one more element, there will be at least 2 elements in TI where you write 1 and you write 0 in SI. So their distance will be at least 3 on that block. And for every block in which SI is not contained in TI, their distance is at least 3. And this is true for most blocks. So if you look at the embedding, it's going to be almost 3 overall because you average over all blocks. Okay. So let's complete the reduction now. So in the yes case, there are these k subsets of size t minus 1 that cover all of E. And then we are going to just build the natural embedding where you look at the embedding of these k subsets, and then we just map it to the closest center, each one. So you look at any set T, which you want to, and so the point corresponding to set T, and that just maps to the SI that covers it. And because of this property of tau, that it's going to be a distance 1 on each block, we have that if you fix some T, and if you fix some block I, then the distance is going to be exactly 1. So let's look at the k-means objective. If we have C log n many blocks, and on C log n many blocks, it's going to be a distance 1. So since we're looking at distance square, it's going to be C log n square times the number of points that we have. Because for every point, the distance to its closest center on each block is 1. And so for every point, the distance to its closest center is going to be C log n. And so the distance square is going to be C log n square. And this is true for every point. So it's times x. So this is the completeness. And in the soundness, let's take some classification, sigma. And we can construct a solution, a candidate solution from sigma to our Johnson coverage problem, where because you're picking, there is this 1-to-1 correspondence between subsets of size t minus 1 and our set of candidate centers, you just go back and pick those subsets, which were picked as your solution in sigma. And now we know that there is this subset E prime of E, which are not covered by S prime. And that is a large fraction. That's 1 minus alpha fraction. So let's pick some subset in which is not covered. And we know that for most blocks, their distance is going to be 3. Okay. And since this is true for most blocks, then we can just assume that tau of t and sigma of t, tau of t are almost 3 distance away once you normalize. So the k-means objective is that for all those subsets not in E prime, we are going to be at distance 1 on each block. So that gives you C log n square because it's distance square. And for every other thing, you're going to be almost 9. So it's like 9 minus little o of 1 times C log n square. And so this, you end up getting like 1 plus 8 log n, because the size of E prime is going to be 1 minus alpha. So you end up getting that because of this expression, size of x E prime is going to be 1 minus alpha, and size of this is alpha. So it's alpha plus 9 times 1 minus alpha. So you get 1 plus 8 times 1 minus alpha. Let me just go back and convince you about the soundness here. So the soundness is going to be t times 1 minus this. Why? Because Alice has t sets, and Alice has t elements, and Bob has t minus 1 elements, and these are not all contained. In other words, Bob has an element that Alice does not have. So when Bob encodes this element that Alice does not have, that encoding can agree with any of the encoding of the universe elements of Alice on at most the distance of the code, 1 minus the distance of the code locations. And since Alice has t elements, you just take a union bound and you get t times 1 minus the distance of the code. Is this fine?
Yeah.
So we have this properties, and the soundness goes through. And so what we were able to show is that assuming the alpha t Johnson coverage hypothesis, in the yes case, you have n prime, and in the no case, you have 1 plus 8 times 1 minus alpha. Of course, if you assume alpha to be 1 minus 1 over E, you get those tight bounds.
So I have one question, Karthik. Okay. So I understand the reduction. What I'm not able to understand, where the communication gain plays a role here. Like why did you not directly go to the, to the embedding thing directly? Is this something which I'm missing here?
So there are two answers to this. One is historical. So the idea came from these things called distributed PCPs, where they had some protocol and they wrote it as an embedding. And so it's easier to think of these things as some protocols, and then the embedding comes out more naturally. Because remember that I described way before here. So this embedding works, but it's in n dimension.
Correct.
And one can interpret this embedding as just the deterministic protocol.
I see. Okay.
And so once you have, I have a deterministic protocol in n dimensions. So can I reduce the message length? And once you notice that the message length corresponds to the dimension, then it's just about coming up with a randomized protocol. So there is this one-to-one. It's connected in a loose level, but it helps to think of these things.
Okay.
Sir, I have one question.
Yeah.
For the containment game that you were discussing as of now, so you shared one deterministic solution, a trivial deterministic solution. So is there any other deterministic solution to the problem?
I think one can show that it's information theoretically not possible. That you need to send at least t log n many bits.
Okay.
Just because, you don't know which the elements are, right? And you want completeness 1 and soundness 0.
But most of the time I see that the information theoretic lower bounds are not very tight in such kind of problems.
Right. So you would be able to show omega t log n, and based on how careful the analysis is, you can put a precise constant over there. But for this problem, it's very, very simple that you should be able to show, I think, at least t minus 5 log n or something like that.
Okay. Thank you.
Okay, so this, so what the proof outline I gave sort of shows the L1 metric here, because we were in the Hamming. And now I want to sort of comment and not go into any proof details of how we get the other results, because all I showed was for the L1 metric. Let me start with how to get it for every LP metric. So what we do is, of course, you can just try to revisit the embedding and do directly from L1 to LP, but you lose a lot. So instead, we look at each block. And in each block itself, it becomes a subset. So whatever we had as the Johnson graph on universe N, what we have done is sort of reduce the universe to size Q. And then we look at embeddings here on Q, because it gives us a crazy amount of runtime. And there we look at embeddings from the Johnson graph to LP metrics. And we just sort of merge it into the protocol that we have. So if we had an embedding of subsets to the Euclidean metric, such that in the yes case, if it's contained, it's a distance 1, and it's not contained, then it's as far away as possible. Then we look at such an embedding and embed it inside the protocol. And that's how we get the tight results for a Euclidean metric, for instance. Okay. And as I said, for the L infinity, we are able to get NP hardness, tight 3.94 and 1.73 in log n dimensional. And we get NP hardness because we use properties of the hard instances of max coverage that were constructed by Feige. And these the properties that are there sort of allow us to do this, because Feige constructs hard instances of max coverage even when the sets are of constant cardinality. And we need those hard instances in order to prove that we have an embedding for L infinity. So that's how we get the L infinity results. And the trickiest part is really the continuous version, because notice that in the continuous version, we don't have a set of candidate centers. So if you think of it in terms of the Johnson coverage problem, we are given as input sets of size T, but we can pick our centers anywhere. It doesn't have to be in layer T minus 1. So what one has to then argue is that if you pick sets in any other layer, then you would not be optimal. Or in other words, okay, you can pick some sets in other layers, but then I can find an other replacement set in layer T minus 1, which is sort of good, like close to optimal. And hence, I can reconstruct from an arbitrary solution a solution of layer T minus 1. And then you can go back to your vertex cover or Johnson coverage problem that we had. So the challenge in the continuous version is because you're not encoding the vertices if you are starting from the vertex coverage or layer T minus 1 explicitly as candidate centers. So the centers can be anywhere, and somehow from the centers being anywhere, we have to decode back a solution for the Johnson coverage problem and then show that we haven't lost much. So that is technically challenging, but things go through in a natural way as we expect. So in some sense, to prove all these results, all these things come together, like these graph embeddings and this communication protocol for dimensionality reduction, and everything comes together in one place. And let me sort of conclude with a small discussion on the Johnson coverage hypothesis, what's known, and then a few open problems. So as I noted yesterday, it's for T equals to 2, this is just the vertex coverage problem, because you have given layer 2, which you can interpret as edges, and you want to find things in layer 1, which are vertices. And here we know that there is an SDP which achieves 0.9292 approximation, and that's tight. But let's look at even the max coverage problem. And one can interpret the max coverage problem itself as you're given as input subsets of layer T, and you want to find subsets of size 1 such that it's covering. And this, so instead of finding subsets of size t minus 1, if we settle for subsets of size 1, then this is exactly the max coverage. And this we know approaches 1 minus 1 over e as t increases. And moreover, if one wants to prove just some LP integrality gap for the Johnson coverage problem, you end up with this amazing question, which is determine the smallest collection of size t minus 1 size subsets that hit all t size subsets. And this is the hypergraph Turan number, and it's been open since the 1940s.
So what's your definition of hitting? It's contained inside that?
Yeah.
Okay, thanks.
And so this is like a tremendously hard open problem. And it was recently resolved for t equals 3. It was a huge, big thing, and it was recently resolved in a monstrous paper for t equals 3. And that automatically gives us improved STP gaps for clustering. So any small improvement here automatically gives us something. So what do we know for the Johnson coverage problem so far? We know for t equals to 2, it's the vertex coverage problem, and that 0.9292 gap, it's not what we expect, but it's going up. And in our paper, we were able to look at layer 3, so all subsets of size 3, and we want to find vertices that hit it. And we showed that 7 over 8 is NP hard to approximate. And because of this, we also get some nice NP hardness results, which almost matches the UGC results that we had.
Karthik, when you say 3 hypergraph vertex coverage, it's like a sets of size 3 and you want to hit them with element of size 1.
Right.
Okay.
And the embedding almost goes through because now you lose a bit more because it's 3 versus 1. So in the yes case, it's a distance 2. And in the no case, it's a distance 4. Instead of ratio 3, you get ratio 2. So the embedding is slightly worse. So what are the key takeaways? It's that we have improved inapproximability of k-means and k-median in LP metrics. And now we use this transcript of this containment protocol to get this. And we also had to do this geometric embedding to go to other metrics. And the main question is if JCH is true. And I've been thinking about this with a few people, and it looks like a tremendously hard problem. Sort of fits into problems that people think will require decades to solve. And so we're trying to write it up now, where we sort of see this in this larger framework that people have of proving tight results for CSP inapproximability with perfect completeness. And this sort of fits into that framework. So at least it seems like it fits in a framework where other things are conjectured to be true. And so let me try to tell a few puzzles like open problems and some really hard open problems. Of course, JCH is probably the hardest open problem coming out of this talk. But let me try to give a few more puzzles that I think should be easily solvable, but somehow seem to elude. So if you look at k-means and the continuous version, so we have a tight understanding. I mean, we have some understanding for everything, but somehow the L infinity metric k-means sort of completely eludes me. I can't prove any hardness. I can't come up with an approximation algorithm that's significantly better. So when we say L infinity metric, so let me rephrase the problem. You're given n points in O of log n dimensional L infinity metrics and an integer k. And we want to find the optimal k clustering. K means clustering of this. You can pick centers wherever you are. And all hardness techniques sort of break. And at the same time, I can't come up with an approximation algorithm that's like, say, 1.5 approximation or something like that. So it's puzzling where the truth is for the continuous k-means in L infinity metric.
And what is a known positive result in L infinity metric?
9.
9. Okay.
Maybe not even 9. For k-means, it's 36, I think. So, and we know that if the dimension is n, then we have an inapproximability of 4.
I see.
So yeah, but even then, when the dimension goes down to log n, there is no hardness or inapproximability. There's no hardness or approximability. So that's a very puzzling thing. And it really feels like a puzzle, not like a very serious problem. The other issue is when we embed into Euclidean metrics, we look at them as points, characteristic vectors, we're getting this 1 versus square root 3. And that's really annoying because you lose a lot of the gap that you get and you get weaker inapproximability results. And yes, one understands that even the approximation you can do better in Euclidean metrics, but is this really tight, like 1 versus square root 3, or can we get better embeddings? Maybe there is an embedding which gives 1 versus 2 instead of 1 versus 3. And so is there a better embedding of the Johnson graph in Euclidean metric? The one direction that I have looked into in this is, what if you put additional structure on top of already things that are there in the Johnson graph? And if you had, like, say, a Boolean hypercube structure, then you can improve this inapproximability from 1 versus square root 3 to, say, 1 versus square root 5. So that gives sort of hope, but then it makes it even worse because already Johnson coverage hypothesis, we don't know the truth. And now we are looking at special structures on top of that. So it makes it less plausible. So this is the other question on Euclidean metrics. And then let me just point out that for K-center, which is studied from the 80s, and for whose hardness of approximation does not require Pcp theorem or any of those things, it's just straightforward gadget reductions, we still don't know the tight answer in Euclidean metric. So if you look at the case where you are given candidate centers, we have square root 3 plus 1, that's like 2.73. And the hardness is square root 7, which is like 2.65. So there is a gap there. And if you look at the case where you can pick centers wherever you want, then we have 2 approximation, and we still don't know how to do better. And the hardness is at 1.82. So this is like a very simple, easy to state problem where there's a gap, and that the gap is there for like 50 years almost now. So this is for K-center. And as Saket was saying, there are these new versions that are coming up. And before that, let me say that K-min-sum, yesterday I said that we can show in general metrics. It's open to show anything in LP metrics. We can just rule out a p-task for now. There is this thing called capacitated clustering, which studied where you can't put as many points as you want into a cluster. So there's a capacity on how many points can be there in each cluster. And here, the best hardness results we know are the ones where for the uncapacitated version. So we don't know if putting a capacity makes it harder or not. So that's the open case here. And I guess this was recently studied in the FPT setting, where they were able to prove a highly non-trivial approximation result of 3. And before that, even constant was not known. So, and then there is this things called fair clustering, where you are given that, okay, you have some colored point set. Let's say you have colored it using C color classes, and you want that in each cluster, not only is your k-means objective minimized, but there's also a fairness constraint that you have, say, one of each color, or each color class is equally well represented, and so on and so forth. And then the question really is, does it make the problem additionally harder, or can you still solve it in the same time? From an approximation point of view, they say that, okay, if the uncolored or clustering version without any fairness constraint can be solved with approximation C, then adding the fairness constraint, whatever the notion of fairness, usually gives them C plus 2 or C plus 3 years, things like that. And then the question is that really needed? Can we prove hardness beyond what is known for fair clustering? Or is fairness just an easy constraint that you can just accommodate approximation wise? Okay, so this is all the open problems. And thank you.
Thanks a lot, Karthik. So before anybody asks some open questions, or other questions, I have a question now. Okay, so if I notice that for a lot of these approximation, there was a paper in 19 by Cohen and other co-authors of him, where they showed that, like these gaps can be met in FPT world, like 1 plus, right? Now, can we have also on your Johnson's hypothesis some assumptions say that even in, say, if I take gap ETH or something, we can't do better than this. Like, is it?
So the problem is Johnson coverage is in FPT.
Yeah, of course, parameterized by T, it is in FPT.
Right. And so we don't know anything from that point of view. And there is no reduction known from gap ETH with that structure.
No, so what do you mean by Johnson coverage is in FPT? When you say it means K plus T.
Johnson coverage is when T is some constant and you parameterize by K.
Correct. Okay, so then fine.
So then we know it's in.
No. Look at vertex cover, no?
Right.
Okay, so what are you asking? So if I'm asking you in some sense that can you cover at least T edges or something with K vertices, no?
Can you cover, right?
And that's,
can you?
So I give you a budget of K.
Right.
And I want you to cover as many edges as possible.
Right.
And that's W1 hard.
That's right. That's W1 hard, but there's a 1 plus epsilon approximation scheme.
Correct. I agree.
So that holds for Johnson coverage as well.
Sure.
And in general, it becomes harder to prove things because K means or K median in Euclidean metric, there is a 1 plus epsilon FPT approximation scheme.
I see. Okay.
And so you cannot expect to prove hardness results because eventually that will trickle down to here.
Sure. Okay. Thanks. Okay. So floor is open for everybody else. Please feel free to unmute yourself and ask questions to Karthik. Okay. So there is, I also know one more clustering constraint which people have studied, something called sum of radii, like, yeah, which I saw.
I saw it in Soda, I think, this year. There was some paper like that.
Yeah. So even before that, there was an old paper by, like, it came from some very good motivation. So the old, so there was a history of for long time, and they managed to get a very good set of approximation algorithm, I mean, like some 10-15 years back.
Mm-hmm.
But there also the capacitated version, it is not known in poly time whether it has a constant factor approximation. And we don't know even any constant factor approximation. So like whether there is an inapproximability of even constant is not known, but we also don't know any constant factor approximation.
Right. To me, the truth, all those places looks like there should be a constant factor. And yeah, so when I study a hardness problem, I make sure that I'm not trying to prove something that's false.
Correct. Sure. Okay.
Yeah.
So that's wonderful. Karthik, is anybody has question?
Yeah. So I was just asking, sir, is there any relationship between Turan number and the property B of the hypergraph?
The property what?
Property B of the hypergraph, that whether a K uniform hypergraph is two colorable or something. Minimum number of edges such that the K uniform hypergraph is two colorable or something like that.
Right.
Or is it the same problem or something?
I think you can formulate it to be the same problem.
So that is what I was saying. Then there are many results there for that, I guess, present for those numbers.
Right, but I think all of those results don't hold in generality, and the bounds particularly don't work. Because there's a huge bound between lower bound and upper bound, and it's an exponential gap.
Yeah, that's true. Yeah.
So the exponential gap is just too much to use any of those bounds.
Okay. Thank you.
So Saket, I have a question for you actually. Do you know if there is any hardness of approximation result known for sum of radii?
Yes, I think for sum of radii, there is a constant factor approximation. And there is some hardness of approximation. Whether they are matching or not matching, I wouldn't know. So
I see. I think it should come out naturally, whatever the right answer from this JCH for that as well.
Yeah, so this is exactly why. Okay. So this is an exercise which I will try to do after your talk, just to understand what JCH is. JCH could do, and explain.
Right. That will be great if more people. So there was a follow-up on GCH by Guruswamy and Sai Sandeep that
Okay.
appears in this Soda 22,
Okay.
where they showed that if you look at the minimization variant,
Okay.
so clearly you can just do a T approximation for any of these problems. And they showed that unlike the hypergraph cases where T is tight, here you can go to T over 2. So they found an improved approximation algorithm.
For this, I see.
It still doesn't violate anything. It's just this
Okay.
that this is you have to be more tricky to play hardness results here.
Here, I see. Just like unique game conjecture.
Yeah, just similar to that.
Yes. Okay. So if there is no question, it was very nice of you to Karthik to give us some insight into this completely new and amazing field of clustering. So thank you very much, and we will be in touch. So enjoy your time in India, and thanks a lot for agreeing to give 2 wonderful talks. It was, as always, amazing listening to you. Thank you very much.
Thank you, Saket, and the organizers for inviting me.
Hi, am I audible?
Yes, Fahad.
So any other organizer here? I want them to make my other system also like co-host.
Yeah, I will make, sir.
Thank you.
Done.
It's, so it looks fine, right?
Do you want to write and try erasing? No, I'm sure it'll be fine. You're on a tablet now, I guess.
Yeah, fine. So I don't know the eraser in the other place, right?
Yeah, I'm not sure if there was an eraser, but then after the talk, I thought maybe you could have just done an undo, or how many ever undos it takes to remove those.
Oh, okay.
Possible. I'm not even sure if that would have worked.
Hmm. Yeah, also like if I want to write something, then it's a bit difficult with the, touchpad.
It makes sense, yeah, of course. Should we just wait for another minute to let people come in? Should we begin, Fahad? You ready?
Yeah, sure.
Can we start now?
Yeah. Okay. Hello, everyone. Welcome back to the second talk of the day. Yesterday in Fahad's talk, he described the central problem in this line of research, and he gave a very rough outline of the proofs. And today we're looking forward, Fahad, to a more in-depth view at the proof techniques that you use to obtain these results. So whenever you're ready, over to you.
Okay, thank you. Okay, so we will continue with the topic, which is deletion and elimination to some specific graph classes. Okay, as I mentioned yesterday, this is based on these two papers. Okay, and in the yesterday we defined this elimination distance and then talked about an algorithmic problem, and we stopped in the midway. Today, we will recall some of these things so that you will all be in sync with what we are doing. And before that, I will give you a bit more intuition or like a bit more motivation towards elimination distance. Okay, and then we will move on. Okay, so just pick a candidate, a well-known candidate vertex deletion problem, which is vertex cover. There's a lot of study on that. So you want to find a vertex cover of certain size. Okay, that's a problem. Or after deleting a small set of vertices, you want the graph to be edgeless. Okay. And for this problem, there are a lot of FPT algorithms known, and a simple branching algorithm will give you an algorithm with running time order 2 to the L into N. You branch on the edges. Okay, this is the algorithm. Okay, now, and this algorithm will also output a vertex cover of size at most L if there is one. Okay, now suppose you have a graph whose vertex cover size is large. Okay, and if you want to find out a vertex cover, then you need to run an algorithm, or like the running time of this algorithm will be 2 to the power your vertex cover number times N. Okay, and when the vertex cover number is large, and this algorithm will be slow. Okay, so then what you can do is you can try for a parameter which is much smaller than vertex cover and try to find vertex cover parameterized by that. Okay, so for example, like this is what I asked. So can we get smaller parameter for finding vertex cover, like which is smaller than the vertex cover? Okay, and then design an FPT algorithm with that parameter. Okay, turns out that there are a lot of them. Say for example, tree width, path width, tree depth. All these width parameters or these structural parameters are less than the vertex cover number. Okay, and in fact, tree width is less than or equal to path width, and which is less than or equal to tree depth, which is less than or equal to the vertex cover number of a graph. Okay, and a simple or a standard dynamic programming algorithm will give you an algorithm for finding vertex cover in time 2 to the tree width to the N. So if your vertex cover number is much larger, but your tree width is small, then still you will be able to find out a vertex cover. So, and if we are going to if we want to find out vertex cover parameterized by these kinds of parameters, then it is also very well to ask about how to finding out these parameters. Say for example, like that is also an interesting open question, right? Okay, and the elimination distance, which I also mentioned yesterday, which is a generalization of tree depth. So in this talk, like we will be more interested in tree depth, and the elimination distance will be a generalization of this one. So think about these three problems: vertex cover parameterized by vertex cover number, vertex cover parameterized by tree depth, and tree depth parameterized by tree depth. Okay, so these are the three problems we get by looking at this deletion version of the problem. Now I will define tree depth formally in the next slide. Okay, we have seen it in the we have seen it yesterday as well. So I will give you first a recursive definition. The recursive definition of tree depth is as follows, right? So if the graph is empty, then there is no vertex, then it is 0. If it is connected, then it is 1 plus minimum of the tree depth of G minus V, where V is a vertex, and the minimum over V. And if G is not connected, it is the tree depth of the maximum tree depth of a component of G. Okay, and so this is a recursive definition, and this also leads to an alternative definition. The alternative definition is as follows. Okay, tree depth of G is the height of a smallest rooted forest F with the following property. Okay, so there is a rooted forest. Okay, and this rooted forest will have n nodes, which is same as the number of nodes in G, and there will be a bijection between V of G and V of F. Think that you are going to place each vertex of G to nodes in this forest F, and there is some constraint. The constraint is for any edge UV in E of G, their corresponding vertices in this forest, which is G of U and G of V, they are in an ancestor, like one is the ancestor of other. Okay, so it should not be like crossing. It should not be like, it should not be, this is not allowed. Okay, so then we say that, okay, so this is what the definition of tree depth. Okay, now as I mentioned, elimination distance is a generalization of tree depth. Okay, now we will define elimination distance to a graph class H, a class of graphs H. Okay, so how do we define it recursively? It is exactly the same way like as tree depth, but here in the first case you will have 0 if G belonging to H. Okay, otherwise it is the same way, like 1 plus minimum over the elimination distance of G minus V if G is connected, where the minimum is over V, otherwise the maximum among the components, okay, if G is not connected. Okay, and I mentioned that this is introduced by Boolean and Dower in 2016, and again similar to the alternative definition of tree depth, we can get an alternative definition of a for elimination distance to H. So it will be, minimum depth or minimum height of a rooted forest. And this time the rooted forest, there will be a bijection from a subset of vertices of G. I will call it X to the nodes of the forest. And look at the graph G minus X, and that G minus X should belongs to the graph class H, and for any connected component in G minus X, the neighbors of that component in G should belongs to a leaf to root path. Okay, so that is mentioned in this yellow part. And if you take any two vertices in an edge whose both the endpoints are in X, then the corresponding vertices in the forest should be like in an ancestor descendant relationship. So this is the definition of elimination distance to H. Okay, so this is an the top is called the elimination forest, and the elimination distance is the height or depth of this forest. Okay, so any question? Okay, fine. Okay, so this is the definition of elimination distance. Okay, now elimination distance is same as tree depth when H contain only one graph, which is empty graph. Okay, so in the bottom you don't have anything. Okay, no vertex at all. Okay, and another thing you can notice is the elimination distance of a graph is at most the size of a minimum deletion set. What do I mean by deletion set? After deleting mod number of vertices, you will be able to get into the graph class H. So how you can see, take this modulator and keep it in a path. Okay, and the remaining, so this is modulator and G minus M belonging to H. So this will be an elimination forest. So there will be some other forest which could be much smaller than this one. So this parameter, which is elimination distance, is less than or equal to modulator. By modulator, I mean the deletion set. Okay, so similar to tree depth and vertex cover number, here I have elimination distance and modulator. Okay. Okay. So there are two questions that of interest, analogous to the case of vertex cover. So what, finding vertex cover and, finding tree depth. Okay. And similar to that, there are two questions, right? So given a graph G and an integer K, can we delete at most K vertices to get into this graph class H? Or like, is the elimination distance at most K? That is the second question. The first problem is called vertex deletion to H. Second problem is called elimination distance to H. So we can ask, these questions on various parameters. Okay. The parameters is, the first one is like, elimination distance to H parameterized by the elimination distance, analogous to tree depth parameterized by tree depth. And the other thing is like, okay, vertex deletion to H parameterized by the modulator size, which is same as, which is analogous to vertex cover parameterized by the vertex cover number. Okay. Or like, the solution size. And the third one is like vertex deletion to H parameterized by the elimination distance. And this is analogous to vertex cover parameterized by tree depth. Okay. So these three questions are of interest. And so now we can, like when you, substitute different graph families for H, you will get to different problems. And this generalizes many problems. Say, for example, this generalizes vertex cover, triangle hitting set, deletion to min degree graphs, say feedback vertex set, lot of problems you can, encode in this one. Okay. Now, first we will consider, like yesterday we considered this one, F-free graphs. What is F-free graphs? So a graph G belonging to is an F-free graph if G does not contain an induced subgraph which is isomorphic to a graph in F, and F is a finite set. So we can call it finite forbidden induced subgraph. Okay. And in the case of vertex cover, F contain only one graph which is K2. Okay. And so we can ask these three questions, like when H is an F-free graph, for example. Okay. So we'll consider that first. Okay. So now take the simplest version of the problem in that, which is vertex deletion to F-free graphs parameterized by the solution size, which is the modulator. Okay. So can we delete at most K vertices to get into this graph class, F-free graphs? And the parameter here is this K. Okay. And here, like similar to, the symbol branching algorithm for vertex cover, we can design a simple branching algorithm for it. Like you just pick an induced subgraph H of G, which is isomorphic to F. This will have constant size, and hence you can find it. And you know that one of the vertices should be in the solution, and so you branch on. So you will get a recursion tree or branching tree with total number of nodes is d to the power k plus 1, and in each node you are going to spend polynomial time. That leads to an algorithm of this running time. Okay, that is the simpler one, which is analogous to vertex cover parameterized by the solution size. Okay. Now ask our favorite question, which is elimination distance to F-free graphs parameterized by elimination distance. This is the question analogous to tree depth parameterized by tree depth. Okay. So given a graph G and K, an integer K, we want to check whether elimination distance is at most K, or we want to output such a decomposition. So just stick to this decision version of the problem. Okay. Now here this K, notice that what we want an elimination forest. Elimination forest may contain lots of vertices, but we want to check whether the height of the elimination forest or the depth of the elimination forest is at most K. The bounded thing is the depth of the elimination forest. And there is no guarantee on the number of vertices in the elimination forest. It could be large. Okay. So that is one of the obstacles to design a branching algorithm, or like to that matter, like to design any algorithm, we see that this elimination forest is too large. Okay. Okay, now just analyze. Suppose you have only, like every elimination forest is very large. Okay, then what will happen is you can find a small separator which separates lots of vertices, which means that in the middle you can find a leaf to root path, and that will separate the left hand side from the right hand side, and you will see lots of vertices from the left hand side and lots of vertices from the right hand side. Yesterday I mentioned that, and we will invoke a result which says that if your problem satisfies some conditions, and then if you are able to solve the problem on graphs which does not contain this kind of separator, which is like small vertices separating lots of vertices, then that theorem or that result is going to give us an algorithm for the problem on general graphs. So the theorem will restrict, it tells that, okay, if your problem satisfies some certain conditions and you are able to come up with a good algorithm on some special kinds of graphs, which is like that does not have these kinds of separation, which automatically implies that your elimination forest cannot contain lots of vertices. So that is a very good thing. And using that structure, if you're able to come up with an algorithm for your problem, then that result will tell us that in fact there is an algorithm for your problem on general graphs. Okay, so more formally, we will define SC unbreakable graph. What is an SC unbreakable graph? It's a graph which does not contain a separator of the following form. Okay, so no separator of the following form. Okay, so a separator of size at most C, that is separating the left hand side from the right hand side, where left hand side contains strictly more than S vertices and right hand side contains strictly more than S vertices. And the result I was referring to tells the following: if your problem can be expressed in a logical fragment called counting monadic second order logic, and for any C there is an S, this S is provided by this theorem or this result. If you're able to come up with an algorithm for testing whether H satisfy this property, whether you are able to, if I'm able to come up with an algorithm for testing whether H satisfy that graph property on SC unbreakable graph, not on all graphs. Okay, here D is a constant which is independent of C, S, and the length of the formula phi, and the constant hidden in the big O notation can depend on the size of the formula C as well as S. Okay, then there is an algorithm of similar running time for testing whether G satisfy that property psi on general graphs. Okay, so the implication of this theorem is the following: if we prove that our problem, which is elimination distance to F-free graphs, is CMSO expressible, and elimination distance to F-free graph is FPT on K, alpha K unbreakable graphs for all K, then elimination distance to F-free graphs is FPT parameterized by K on general graphs. Okay, so to get an FPT algorithm for our problem on general graph, we need to prove these conditions A and B. Okay, now yesterday we went on and saying that indeed the condition A holds. Okay, to prove the condition A holds, I said that we can, this problem, elimination distance to F-free graphs, this problem can be characterized by, this problem has a different characterization that will allow us to say that this is CMSO expressible. So I will write down that, I will note down or recall that characterization here, which is elimination distance of G, elimination distance to F-free graphs is at most K, if and only if the following hold: there exists a vertex subset X such that G minus X is a free graph Okay. And torso of X is F prime minor free. What is torso of X? Torso of X is like this is X. It is a vertex, it is a graph on the vertex at X, and you have an edge between two vertices in this graph. If in your graph G, there is a path from these two vertices where the internal vertices are outside X, and that graph is called a torso of X. And torso of X can be expressed in monadic second order logic, and F minor, like test this property F prime minor free, this can also be written in monadic second order logic, and F free, this can also be written in monadic second order logic. And hence you can write a formula in monadic second order logic for testing whether elimination distance of G is at most K or not. Here I want to point out that this F prime will depend on K. Okay, and hence for every K you will have different formulas. Okay, so your problem is expressible in CMSO. This implies that the first condition is done. Okay, now what we need is, and that is yet to prove, is elimination distance to F-free graph is FPT on these special kinds of graphs, which is K alpha K unbreakable graphs. Once we prove that, we are done. Okay, so now what I'm going to do is I'm going to give you a proof for this. Okay, the second one, and it will be in detail. Okay, so we want to design an algorithm for elimination distance to F-free graphs on this, like we assume that our input graph is K alpha K unbreakable. Okay, now suppose my input is a S instance, okay, which means that the elimination distance is at most K. Now look at a hypothetical solution which look like there is an elimination forest of depth or height, or depth at most K, and you will have lots of connected component after deleting this X, and each connected component is going to see only from a leaf to root path, and all other edges will also be from leaf to root path kind of thing. Okay, so this is the this is what we know if this is a yes instance. And since the graph the input graph G is K alpha K unbreakable, immediately we get that the cardinality of X is bounded, or the number of vertices in this elimination tree is bounded. Suppose it is more than this number 2 alpha K plus K, then somewhere in the middle you can take a leaf to root path that will that will separate the left side from the right side vertices, and there will be more than alpha K vertices in the left and more than alpha K vertices in the right. Okay, so that will contradict our assumption that G is K alpha K unbreakable graph. Okay, and so that is the first implication. So this the size of the tree is at most X. This is at most bounded by a function of K. And now if you look at the job these vertices which I'm going to play, which will be in these tree nodes do, this will be used to maybe kill an induced subgraph in G which is isomorphic to a graph in F. So it may be used to hit on those, okay, or kill on those structures, or it may be doing a job to disconnect many graphs, right? To disconnect graphs. So one of these two jobs it will be doing. So it may not be doing this alone, it may be doing it with the help of other vertices, but every vertex will have a role which will be towards one of these, right? Either killing an obstruction or to make more connected components so that the depth of the tree won't grow. So these are the things each of these vertices in X is going to do. Okay. Now what we are going to do is we are going to design a branching algorithm for our problem. Okay. So the immediate thing you can branch on is what? Like, okay, before going to like explaining how to branch on, first let me tell you that look at this X, look at this elimination forest. This elimination forest has bounded size. I mean, the size of it is bounded by 2 times alpha k plus k. Okay. And then I can guess the structure of this forest. Okay, like how this look like. Okay, so I don't know which vertex from G will be a root vertex or the first neighbor of the root. This I don't know, but structure I can guess. Okay, that is, you know, an f of k guess. Okay. Now, after guessing that, what I will do is I will check whether my graph G has an obstruction, which means that an induced subgraph which is isomorphic to a graph in F. Okay, if no, then we are done, right? The graph G itself is, you know, is F-free. So if we find such a, like we can find if there exists some obstruction, then what we know is at least one vertex from that subgraph, induced subgraph, should belongs to X, should be part of this forest. Okay, so what I can do is what I can guess or I can branch on that vertices, and these vertices may be placed in one of these locations in this tree. Okay, and I can branch on the positions of that tree. Okay, so maybe like the vertex V could be in the position like the third neighbor of the root. Okay, so I can branch on them. So because the number of positions in the tree is bounded by a function of k, and the number of vertices in the obstruction is a constant. Okay, so you just branch on them where it goes to. Okay, so what you do is after, you know, you keep finding out obstructions. After, you know, some vertices you will fix on the tree and look at the graph, which is, you know, G minus the vertices fixed on the tree. And if there is a, you know, obstruction, which is an induced subgraph, which is isomorphic to a graph in F, then you know that one of the vertices should go into X or going into the elimination forest, and the positions are bounded, so you branch on them. After doing all these, you know, we will have, like, after exhaustively doing this branching, like what we will have is like, you know, this elimination tree, this is partially filled. The partially filled locations are marked red, and other locations are not, you know, the locations which are not marked red are vacant. That is expecting some, you know, vertices from G minus these filled vertices. Okay. Now, what I know is in G minus these red vertices, there is no obstruction. That is actually F-free. This I know. Okay. Because if there is an obstruction, I will branch. Okay. So in G minus the red vertices, red filled vertices, that is actually F-free. But it may not satisfy the property we want, which is like any connected component from the bottom can only have neighbors from a leaf to root path. That property may not be met. Okay. So suppose there is a component which see 2 neighbors in this forest, 2 filled neighbors. Okay. And they are not in the not in an ancestor descendant relationship. Okay. Then look at a path from those 2 vertices through that connected component, which is marked below. Okay. I know that, you know, in my solution, at least one vertex from this path should go into the top. Okay. Go into the elimination forest. Okay. Because otherwise we will not satisfy the required condition for elimination forest. Okay. Okay, so now I claim that, now look at this path. Okay, look at this, the internal vertices of this path. and first alpha k vertices and last alpha k vertices. I claim that one of these vertices from A union B should be in the solution, like it should be in this elimination forest. And can someone say why it is? If it is not, then I say that the graph we started with will not be K alpha K unbreakable. Okay. Now, why it is? Suppose none of these vertices in A or B is not in the solution. Okay, not in the elimination forest, which means that after I deleting my elimination forest, I will have a connected component. That connected component will like I will have lots of connected component, where one connected component will contain these vertices and one connected component will contain these vertices. Now, if I take this set of vertices, this set of vertices will separate A from B. Okay, this connected component from this connected component. And that tells that there is a separation which separates, A from B, and both A and B are of size at least alpha K, or like, I will put +1 here. Okay. Okay. And the separator size is at most K. That will contradict, our assumption that my input graph is K alpha K unbreakable. Okay. So, so what you do is, if you see a connected component which is going to have neighbors which are not in ancestor-descendant relationship, then 2 alpha K vertices to branch on, so you branch on. So after you do all these branching, what is the property satisfied? Every connected component in the bottom, which will be F-free, and they are going to see only from one leaf to root path, the neighbors in one leaf to root path, and that completes an FPT algorithm for this problem. Any questions?
Yes. So if I understand correctly, abstractly, are you showing the following problem FPT in K alpha K unbreakable graphs, that given a graph G and let's say a forest on K vertices, whether it is an elimination forest?
Correct. So forest is given and you need to map vertices from G to this forest.
But what is the complexity of the problem in general graphs? So given a graph G and a forest on K vertices, the question is it, and you are also given this capital F, then is this forest an elimination forest for F?
So this algorithm will not give that because we are branching on the number of positions in the forest also, because we want the number of positions to be bounded. If the number of positions is bounded, then yes. Or the number of vertices in the forest is bounded, then yes.
Yeah. Number of vertices in the forest. I'm saying you are given a graph G and a forest on K vertices.
Yeah.
Okay.
Forest on forest with the depth K, and number of vertices in the forest will be some function of K bounded by.
Yeah. I mean, K, by K, I mean really F of K, whatever. Right?
Okay. Yeah. And
So,
then you are going to get an FPT algorithm by branching.
But not in general graphs. You are still also using.
Okay, correct. Not in general graph, but in K alpha K unbreakable.
Right. But what is known about that problem in general graphs?
I don't know actually.
So Fahad,
I think you can apply the previous theorem, the Lobsnow et al., and get FPT, what you are asking. So you are asking an elimination forest of a specific kind, right?
Yeah.
So that this algorithm won't give you, right? And I think you could apply the Lobsnow et al. Theorem and prove that it is CMSO and prove only on K alpha K unbreakable graphs, and then probably get it. because this is bounded size, you are talking about the tree. So you have an additional condition that, torso of X is at most, tree, is F prime minor free, and there is a tree embedding of for X with some certain properties.
Okay. So essentially that's what you have shown. So you're essentially saying in any graph, if you're given a k-sized forest and you want to know whether it is an elimination forest for an FV class F, then it is FPT, because you just apply that black box of unbreakable and then do what you just did now, doing this mapping.
You need to prove this condition A and B, where A is CMSO, that you can prove because that is tree is bounded size, and B you do as I explained here. Because this condition hold. Okay, and there will be a bit of catch, I think there is a bit of problem there, because the tree size is depending on this alpha k, which that theorem is going to say. So probably I really don't know. So that might be a problem.
No, but tree size is a function of k only, right?
No, but this alpha k is provided by that result.
True.
And if you have if you are yeah, correct. No, you can apply. You're right. Because we are asking about the connected component size in the bottom. Yes, you can apply that. Okay, then I will. So we proved the condition A as well as condition B, like these two conditions we proved, and this gives elimination distance to F free graphs is FPT, and parameterized by K here is elimination distance. Okay, that is what we did. Okay, so what we got is like elimination distance to F free graphs parameterized by elimination distance is FPT. So it's similar to tree depth parameterized by tree depth. Okay, and the other we already which is a simple branching algorithm. Okay. Now there is a third question, which is vertex deletion to F free graphs parameterized by elimination distance. Okay, like vertex cover parameterized by tree depth. Okay, we'll answer this at the end. Okay, I will not give an algorithm, but I will answer this at the very end. Okay. Now let's move on to another class. Suppose H is F topological minor free graphs. Okay. Now I will define, F topological minor free graphs without, going through these minor definitions. Okay. So in the F free graphs, what we want, suppose H is a graph in F. We don't want this graph H as an induced subgraph in my graph. So G is an F free graph if, say, then suppose H is the only graph in F, then we don't want this H is an induced subgraph in F. Okay. And now suppose I ask about F topological minor free graphs for F containing only one graph, which is this H. Okay, then the meaning of it is you take all infinitely many graphs which are subdivisions of this H. So one example of a subdivision of H is shown here, which means that on an edge you are allowed to put many vertices. Okay, like this subdivide edge. Okay, you may not subdivide all the edges, you may not subdivide edge at all, but like that will give you infinite number of graphs. Okay, a subdivisions of edge. So you may be subdividing once, twice, thrice, million times. Okay, so that will give an infinite family of graphs. Okay, and a graph G is F topological minor free if any of these subdivision of H should not be present in G as a subgraph. Okay, so that is an alternate definition rather than going through minor or that definition. So look at the subdivisions of H. So there will be infinitely many such graphs. And these patterns should not occur in my graph G as a subgraph. Then I say that G is F topological minor free. Okay. So now automatically, like the problem is like these patterns are infinite in number and infinite in size. Okay, so we can't simply branch on them. Okay. Again, we can ask these three important questions: vertex deletion to F topological minor free graphs, parameterized by the modulator size, and elimination distance to F topological minor free graphs, parameterized by elimination distance, and vertex deletion parameterized by elimination distance. And for the first problem, there is an FPT algorithm which is very recent, and there is no simple algorithm like what we have seen for the previous case, and this is a very complicated algorithm. Okay. So to to adapt that is very difficult thing. So what we are going to do is we want to solve the second problem, elimination distance to F topological minor free graphs. We are going to use the first algorithm as a black box. We are not going to adapt anything. We just going to use black box, this algorithm as a black box, and then going to solve elimination distance to elimination distance parameterized by elimination distance. Okay, so that is the plan. But still, it is also a branching algorithm. At the bottom of the branching, we are going to apply Fomin-et-al's algorithm for deletion version of the problem, parameterized by deletion set. Okay. Now again, the pattern is same like what we did for F free graphs. The pattern is like apply Lobson-Overton. Okay. So what we need, we want to prove that my problem is CMSO expressible, and there is an algorithm for the problem on K alpha K unbreakable graphs for all K, and where K is the elimination distance. Okay. And if I prove A and B, then by this theorem or by this result, we are going to get that our problem is FPT on general graphs parameterized by elimination distance. Okay. So the pattern is same. So now elimination distance to F topological minor free graphs, we can prove that it is CMSO expressible. So for that, we come up with a characterization when it was F free. Similar kind of characterization we can come up with for this problem, and it says that if the elimination distance is at most K, elimination distance is at most K if and only if it's both the direction. If there exists a vertex, if and only if there exists a vertex subset X such that the first property, this property is same, and G minus X is topological minor free. That's the only thing. So, as I mentioned, F prime will depend on K. Depends on K. And so, and these characterizations can be expressed in this particular logic. And because of that, A is done. Now we need to prove B. Okay. So again, come back to this case. In the case, come back to this particular case. Okay, K alpha K unbreakable graphs. But here we want to get into F topological minor free graphs. Okay. Now, again, by the same argument, the cardinality of the number of vertices in this tree is bounded by a function of K. Okay, that goes the same kind of argument. And then suppose this is a hypothetical solution and it looks like this, then I claim that there is only one large connected component in G minus X. Suppose there are two large connected components. Suppose this was also large. Then what will happen is this yellow thing. Okay, this path is going to Yeah, this path or this separator is going to separate this yellow from that purple. Okay, and both the yellow and the purple are large, which will contradict, unbreakability. Okay. So, which means that, there can't be two large connected components. Now, can there be no large connected component? That is also not possible. If there are lots of, like I assume that the graph contains lots of vertices and X is bounded size, and if all the connected component in G minus X is, has small size, like which is less than alpha k, then somewhere one of the leaf to root path will be a separator contradicting the fact that my input graph is k alpha k unbreakable, because many of these connected components I can push to the left and many of them to the right by taking an appropriate leaf to root path as a separator. Okay, so this tells me that there is a unique component in G minus X where X and this tree is a hypothetical solution. Then there is a unique component in G minus X which contain more than alpha k vertices, and the remaining will be all small components. Okay. Now, what we are going to do is we are going to design a branching algorithm where we are going to, like, first, what, as we did before, we will guess the structure of the tree. After guessing the structure of the tree, what we are going to do is we will come up with a branching rule, and that will place the vertices from the large connected component to this particular root to leaf path. So I guess this structure of the tree and this particular leaf to root path, which is TR, where this unique component is going to see, like unique component is going to see to have neighbors from this path only. Okay, that path also I guess. Okay, which is that path. Okay, so then what we are going to do is we design a branching rule, and that branching rule is going to find out vertices, and that will be placed in this particular path. Okay, and at the end we are going to solve the deletion version of the problem and some more trivial branching. Okay, so that is the high level overview of what is going to do. Okay, now I'm going to explain it in detail. Okay, so as I mentioned, we are going to guess the structure of the tree and which path is this special path where in my hypothetical solution, the unique component is going to see have neighbors. Okay. Okay. Now, to design a branching rule, I want to talk about something called, alpha k connected set. Okay. An alpha k connected set in a graph D is a connected vertex subset B. What do I mean by connected vertex subset? The graph induced on B, so is connected. So here it will be D of B connected. That is the meaning. Such that the following hold: the cardinality of B is at most alpha k, and neighborhood of B is at most k. So it will be like in a graph, a small vertices, small set of vertices, and if I look into the neighbors, this is also small. This may be large. So this is what this B is called connected set. Okay. So pictorially, it looks like this. Okay. Now, and we say that, okay, this connected set is maximal if there is no other alpha k connected set B prime, which is a superset of B. Okay, then we say that it is a maximal, connected set, maximal alpha k connected set. Okay. Now, there is a result which says that the number of alpha k connected sets in a graph is at most 2 to the times this quantity times n. Okay, so this is actually linear in n and FPT, number of them, and it can be enumerated efficiently. Okay, so this is now. Okay, Now what I'm going to do, branching is simple. Okay. So initially what we have, we guess the structure of the tree or the forest, and we also guessed this special path T to R. And G is at the bottom. Currently G is at the bottom because we didn't place any vertex from G to this path or this forest. Yeah. So enumerate all the maximal alpha k connected sets. And if one of them, pick any one of them and then check whether that is F topological minor free. Okay, so that we can check easily. Okay, because there are algorithms to test that. Okay, so pick a maximal. So enumerate all the maximal alpha k connected set and check whether there exists one such that the graph induced on the neighborhood of B, which has bounded size. How much size? Alpha k in B, and its neighbors will be k. Okay. So in this graph, so the graph induced on neighborhood of B, it will have size alpha k plus k. And if it is not topological minor free, then what we can say, at least one vertex from this should be going to the elimination forest. Correct? Okay. So you take any alpha k connected set B, okay, not even maximal. Okay, then if it is not F topological minor free, then at least one vertex from that close neighborhood of B should go into the forest part. Okay, and because of the maximality, we can prove that there is one vertex that should be placed in this special T2 root path, and that can be proved using maximality. Okay, so I will not explain in detail, but you use maximality to prove that. Okay, so what do? You branch on them. You branch on B union N of B and the positions of T to R path. Okay, so you keep doing this, and at some point it looks like this, right? So you keep doing it, and what is the second time how you do? You look at there will be only one, at any point in time, there will be only one large connected component, and you try to enumerate all, let that be D. You try to enumerate all the, maximal alpha k connected sets in D. And if one of them is not F topological minor free, you try to branch. Okay, keep doing that. Okay, that's what you do. Like that you are going to do on that unique, there will be a unique connected set at any point in time that is going to have this property. Okay, so you do this branching, and after exhaustively doing this branching, what you will have is in this D, all the alpha k connected sets are not F free. So they are all F topological minor free. Okay, and then all these small connected components here that may not be F topological minor free, but the number of vertices here will be bounded by alpha k. If it is not bounded by alpha k, then again you can prove that our graph G is not unbreakable. Okay, it is breakable. Okay, that you can prove. So after exhaustively doing our branching, we look at all the small component and here in the bottom, their size will be at most alpha k. You guess where these vertices will go, like some of the vertices should be placed in this elimination forest. You guess it. Okay, and then in the final step, what you do is you will solve vertex deletion for F topological minor free graphs on this large component with the parameter k prime being the k minus the number of filled vertices, k minus green. Okay, now once you find that, what you will do is you are going to place that vertices in some order here. That's it. Okay, so that will give you, that is going to give you an elimination forest for the graph. Okay, now why that is correct? Because we branched on all the connected sets of small size, which is not F topological minor free, and all the small components which is outside this part, which is going to have an F, which is going to have a graph from F as a topological minor, will allows us to say that there will be something which is this connected set which is F, not F topological minor free, and using that we can prove the reverse direction. And what we will get is, like, at the end we just do one execution of the vertex deletion problem, and if we are going to get an S answer, like whatever the vertex set we are deletion set we are going to get, we just place that in this field location, and that's going to give you elimination forest. Okay, so any questions you have? So we are going to find some small connected graphs, and we are going to branch, like if it is not F free, and after exhaustively doing that, we are going to do one invocation of the vertex deletion problem parameterized by the solution size, like the modulator, and then place it. Okay, so this leads to, so this is the algorithm, and I didn't explain how the reverse direction works, but mainly using, for the first one it is maximality, for the second one, if we don't have these kind of things, then what, if there is a solution, any solution for this problem can be placed there. Okay, so assuming this is not possible, we'll prove that any vertex deletion to F topological minor free of size at most k prime can be placed here in this special route to leaf path, and then get a solution. Okay, so this proves elimination distance to F topological minor free graphs parameterized by elimination distance is FPT. And again, we have the third question: what about vertex deletion to F topological minor free graphs parameterized by elimination distance? How much time I have? I think I passed the time. So how much more time I can take?
A few more minutes, let's say 5 minutes, Fahad. Would that be?
Yeah, 5 minutes is good enough. Okay. So what we proved is, okay, now where did we use that, it is F topological minor free? Like, one is to solve this one, right? So if I have a problem, like if I have a, graph class H for which vertex deletion to H, parameterized by modulator is FPT, then can we get an elimination distance? Not quite, because we also used the theorem by Loxanov et al. There it says that it should be CMSO expressible. So we could say that, okay, if my graph property has CMSO expressibility and it has, an algorithm for vertex deletion parameterized by the, deletion set size, then probably we will be able to, do the same. And there is actually a bit more things we need, which is to prove here, and that two conditions are, it should be a hereditary graph class and closed under disjoint union. What do I mean by closed under disjoint union? If I take two graphs G1 and G2 in H, then G1 disjoint union G2 should be in H. And what is hereditary? Every induced subgraph of, like, if G is in H, then every induced subgraph will also be in H. Okay, and these two properties we will use in this algorithm at the end to prove the reverse direction. Okay, like here, like at the end, like for our unbreakable case, these two properties, we need these two properties to prove the correctness of this one if H is some special graph classes. Okay. And so CMSO, because of Loxonow et al., and hereditary and closed under disjoint union, because we need that one to prove the correctness of our algorithm. And then, so we will get a more general result, not necessarily just for F topological minor free graphs, but take any graph class H, which is hereditary, CMSO expressible, and closed under disjoint union. Then vertex deletion to H is FPT parameterized by, and this condition, because we want to invoke at the end that deletion version of the problem, and then we will be able to get this one. Okay, and everything is same. I just took a candidate example being H equal to F topological minor free. Okay, the properties we use are these three. So you just substitute, these four. You just substitute these four and you can prove. Okay, by just verbatim going the same way. Okay, and then we had the following question, right? Vertex deletion to H parameterized by elimination distance. Okay, once we get an elimination forest, we can use that elimination forest to prove this theorem: vertex deletion to H parameterized by elimination distance. So intuitively, you can think that on tree width, if tree width is bounded or tree decomposition is given and your problem is CMSO expressible, then you will be able to get a good algorithm. And here we have CMSO expressibility and we have an elimination forest from which, like, these two together with some additional work, you can prove that vertex deletion to H parameterized by elimination distance is FPT. Okay, and this gives us the following result, which means that let H be a hereditary graph class and CMSO expressible and this property hold, then all these problems are equivalent. Vertex deletion to H parameterized by modulator is FPT, implies that elimination distance to H parameterized by elimination distance to H is FPT, and this implies that vertex deletion to H parameterized by elimination distance to parameter is FPT. And why this is this? I say this implies this. Why it is so? 3 implies 1. So we proved using 1, we proved 2. Using 2, we proved 3. Now, if it is equivalent, I want 3 implies 1 also. How do I get 3 implies 1? Any quick answer?
H is smaller than
correct.
H.
The parameter in 1 is more than the parameter in 3 because of that. Okay. So actually what we proved is in terms of FPT, they are all equivalent. Now suppose what is the implication of this? Suppose you want to prove that vertex deletion to a particular a class of graphs is FPT parameterized by elimination distance. You probably even don't need to know the definition of elimination distance. You need to prove, if you are able to prove that it has these properties, and design an FPT algorithm for the plain deletion version of the problem parameterized by the solution size, you are going to get all of them. Okay. And H being hereditary graph class, CMSO expressible, closed under disjoint union, these properties is symbol properties, and for many graph classes this hold. For example, we have seen topological minor free, F free. So if H is caudal graph, it holds. If H is say interval graph, it holds. If H is bipartite graph, it holds. So if H is such that every connected component is either a planar graph or a bipartite graph, this property holds. Okay. So for a lot of various problems, you can say that you just need to prove, the plain vertex deletion version parameterized by, the deletion set for the modulator is FPT. And that will give you, FPT for all other kinds of parameterizations. Okay, so in that sense, it is a a very strong result. Now, let me conclude. Okay, so all the algorithms I explained here, like the main algorithms I explained, are non-uniform, like not the algorithm on unbreakable graph, algorithm on general graph, and the unbreakability comes from the CMS or thing, like, and like applying the condition A. But we can get uniform FPT algorithm when H is F free, F minor free, or F topological minor free, when all the graphs in F are connected. Okay, so that is a condition which I didn't mention yesterday for a question. So if all the graphs in F are connected, then we can get a uniform FPT algorithm. Also, we can get a uniform FPT algorithm when H is a chordal graph or bipartite graph or interval graph. This will not be subsumed by any of these F free, F minor free, or F topological minor free class. Okay. And fast algorithm, like now we can ask, like, what about running time? I just said FPT, and this running time is huge. Like F of whatever that parameter is, that function F is huge. Okay, and also it is non-uniform, right? For many of them. Here there are uniform things, but still it is huge running time. Okay. What about like single exponential or 2 to the polynomial in the parameter, like those kinds of running times for specific classes of graphs? That is an open question. And similar to elimination distance, which is a generalization of tree depth, even at all, like introduced the H tree width, which is a generalization of tree width. Our results extend to these parameters as well. And we get a result which says that pretty much all deletion, elimination, H tree width version parameterized by any of the other parameters is FPT. Like all these are equivalent, like not FPT, they are all equivalent. You need to prove only one. Here only one is missing, which is, I think, elimination distance param by H tree width. This is missing. Okay, so this we don't know whether can be added to this one. That is also an open question, but this keep apart and all other versions, right? All the problems, like whatever, like, and with various cross parameterization, they are all equivalent. You can prove that they are all equivalent. So in terms of FPT, it is all same as, whether the plain vertex deletion version parameterized by solution size is FPT or not. Okay, that I will stop here. Any questions?
Thanks a lot, Fahad. Let me applaud on behalf of everyone. Yeah, so we have time for a quick question, I suppose. So Fahad, what is your belief about this missing case?
Which one? Sorry, I didn't get it. No. Oh, I'm not able to listen to you. So others are able to.
We can hear you, Fahad. I think
MS sir was speaking.
Yeah, I think he asked, what is your belief about this last?
Oh, okay. Last belief is that will fit into this theorem. That will also be equivalent. Since all these are equivalent, which, yeah, it looks like it will also be equivalent. Any other questions? Okay, I think MSR's audio is not working.
Yeah, he sent the chat message saying thanks. And
okay, then bye. Thanks.
Okay.